Okay, so you know what a solution is at this point. You know what an aqueous solution is. It's a solution with what as the solvent? Water. Aqueous. And what we're going to talk about is how ions behave in aqueous solutions. A lot of the chemistry that you've done up to now has been you've been doing the behavior of ionic compounds in aqueous solution from nearly day one. But now you kind of have enough background that we're going to talk a little bit more about what it looks like. So, when you take an ionic compound, we could use salt, for example, and you stick it in water. It behaves in a very particular fashion that governs how that solution then behaves. What happens is called dissociation. So the ions actually separate, and we can write an equation for this. So let's practice this. First of all, let's look at what this really looks like. What do you know about water? Tell me something about water. You are going to remember that for the rest of your life, and I will be very happy to hear it. It is attracted to only two things in the whole world, itself and everything else, but it's also polar. Remember, it's got those regions of partial charge. Mickey's little ears are positive because oxygen is very electronegative. It strips away the electron cloud, and so the oxygen ends up gathering most of the electron cloud. The oxygen end is very negative. The ear end is mostly just two little protons sticking off the top. Because it is charged, it is really good at getting in between these other charged particles. And this is in fact why water is such an effective solvent for ionic compounds, because it gets right in there and it's got regions of charge, so in essence it can surround the positive and negative charges, you know, the little chlorines and the little sodiums, with water molecules. And that's I kind of try to show that here, that the little positive molecules will be surrounded by Mickey ears pointing in at them, and the little negative ones will be surrounded by little Mickey chins pointing in at them, because it's just a charge issue. So when we write that equation to show the dissociation of an ionic compound, and it is really I should be careful. It's an equation, but it's not a chemical equation. We're not talking about a reaction happening. There is no reaction happening here. No new chemicals are being formed. No new partnerships are being formed. We're just breaking apart an ionic compound. So we have solid NaCl, and if we put that in water, what do we get out of it? Well, we get Na1 plus ions in aqueous solution, and we get Cl1 minus ions in aqueous solution. Okay? Add up the charges on the front side of that. Are there any charges? No, so it's neutral overall, right? Add up the charges over here. We got +1, we got -1. Is it neutral overall? Yes. Charges have to be balanced because the formula for the ionic compound coming in obviously had balanced charges. So we had an equal number of positive and negative charges. Let's do one. I won't say it's trickier, but it's just more interesting. Let's do magnesium chloride. We can dissolve that in water. So we come in with solid magnesium chloride. 1 mole of solid magnesium chloride is going to dissociate into what? Give me one of the ions that we're going to see out of this dissociation. Did you say magnesium 2+? I thought that's what I heard. So we're going to get 1 mole of magnesium 2+ ions in aqueous solution. How many moles of chloride 1+ ions are we going to get? 2. We're going to get 2 because for every 1 magnesium atom, there are 2 chlorine atoms. So we're going to get 2 moles of Cl1 minus also in aqueous solution. So let's check ourselves here. Do we have equal numbers of atoms on each side of the equation? Yes. 1 magnesium, 2 chlorine, 2 chlorine. Are the charges balanced? Yes. It all ends up being neutral. Do you see? Does that make sense? Okay, so if this doesn't seem intuitive, remember that in reality, we write MgCl2. What that means is you've got one magnesium ion holding, standing shoulder to shoulder with two chloride ions. We write it as a simple compound. When that breaks apart, you have one magnesium for every one magnesium that goes out into that dissolves, that goes dissociates. You have two chloride ions that do the same. Does that make sense? Okay. Okay. If I take this stuff, ammonium phosphate, multiple polyatomic ions. What would that break up into? Okay, so we know already that this is going to break up into ammonium ions in aqueous solution, and ammonium ions are 1 minus, and some PO4, oops, 1 plus. Jeez Louise, Moser. PO4 3 minus, also in aqueous solution. Now, the question is, how many of each? How many ammonium ions are we going to get out of every mole of ammonium phosphate? You can vote with your fingers. So we're going to get 3, and we're going to get 3 because of this. Because for every phosphate ion, there had to be 3 ammonium ions to balance it. So it's a little bit like balancing a chemical equation, though remember there is no reaction happening. We can do the same thing that we've done for chemical equations, though. What did I just do? I just erased the leg of the P. That was silly. And we can look at the ions individually. Well, we have 3 of those. We have 1 of those. NH4, we have 3 of those. PO4, we have 1 of those. We can do that. And if you need to, that's totally reasonable. But again, if you look at the number of individual ions and atoms, balanced. If you look at the number, the charges, balanced. This is neutral. They balance one another out. Here we have 3 times positive 1 is, plus 3. And here we have negative 3. They cancel, which we would expect because these things canceled and formed a neutral compound in terms of their ionic compound. Questions before we go on? So that's writing a dissociation equation. That's all there is to it. You take an ionic compound, it's a solid, you dissolve it in water, and you write down the ions that you get. This is actually a form of stoichiometry. It would be, dissociation stoichiometry. It's kind of the lowest grade stoichiometry we've done. If you want to look at the practice on 426, you can, though we've kind of done a few practice problems. I think you kind of get it. But let's, here are the kind of questions that can be asked. How many moles of ammonium ions would we get out of 1 mole of ammonium phosphate? 3. We get 3 moles of ions. How many total moles of ions would we get dissociated out of 1 mole of ammonium phosphate? 4, because we'd have 3 moles of ammonium ions and 1 mole of phosphate ions. So that's really all there is to the dissociation stoichiometry. Okay, now, haven't you always wanted the power to tell the future? Haven't you always wanted to be able to predict if something will dissolve in water or not? Never fear, you can! So, if you grab a chem book, page 427, we're going to practice predicting solubilities. For your party trick, what you need to know about predicting solubility. All the compounds are classified based on their components. So if it's sodium chloride, if it's sodium bromide, if it's sodium phosphate, it's a sodium compound. If it's magnesium phosphate or calcium phosphate or iron phosphate, it's a phosphate compound. So you're looking at the individual components for the compounds. What's interesting is, in terms of solubility, there tend to be similarities among, phosphate compounds, sodium compounds. And these guidelines here just talk about the individual families. So, for instance, most sodium, potassium, and ammonium compounds are soluble in water. Most nitrates, acetates, and chlorates are soluble in water. Then we start to get into things that have exceptions. Most chlorides are soluble except silver, mercury 1, and lead. Lead 2 chloride is only soluble in hot water, not in cold water. Most sulfates are soluble except barium sulfate, strontium sulfate, lead sulfate. Most carbonates, phosphates, and silicates are insoluble except, so we start to get into those exceptions. What we're going to do is practice predicting solubility, and then you'll tell me which rule you're basing your prediction on. So you can work in teams on this. So I'm looking at ammonium nitrate. So this is both an ammonium compound and a nitrate compound. And if I look at my rules, it says that most ammonium compounds are soluble, so I would say yes to that. There's no exception. It also says most nitrates are soluble, so it's a double hitter. It's good on all grounds. I would say ammonium nitrate is soluble, and yeah, it's highly soluble in water. Okay, which team wants to take ammonium sulfide, NH42S? Okay, and she says it is soluble based on 1 because most ammonium compounds are in fact soluble. And she also says it's soluble because of rule number 6. Most sulfides are insoluble except ammonium sulfide. So yeah, ammonium sulfide is in fact soluble. Okay, who wants to take CaCO3? What is that stuff? I heard somebody say calcium carbonate. Insoluble, he says, based on what rules? Rule 5. Most carbonate, phosphate, and silicates are insoluble except sodium, potassium, ammonium. It is not one of those exceptions. And in fact, calcium carbonate is not soluble. Calcium carbonate, incidentally, is the stuff that makes up sea creature shells, so like clam shells, mollusk and bivalve shells. If it was soluble, they would have a very difficult time of it because their shells would dissolve in the ocean water. So it's a good thing it's not. Okay. Silver chloride. Take it. Okay, so he says insoluble based on rule 3. Most chlorides are soluble except silver. So yeah, not soluble. And what about barium sulfate? Who wants to take barium sulfate? Okay, so he says insoluble based on this. Most sulfates are soluble except barium. This is pretty easy. This is not hard. It's all rule-based. The only thing you have to be careful about is those exceptions. I've done that myself where I go, oh yeah, it's a carbonate. It's not soluble. Oh shoot, it's sodium carbonate. Yeah, it is. So that's all you really have to watch out for is checking your rules. And generally we just designate, yes, it's soluble. No, it's insoluble. Let's see, what was our first insoluble? No, it's insoluble. And after you've done some of these, in terms of practice, it gets almost automatic. Like nobody's going to have to ever, yeah, ammonium nitrate, yeah, that's super soluble. Okay, I'm going to assign a couple of homework problems. The big skills for today are this. Writing dissociation equations, I apologize, dissociation, and predicting solubility. Well, not tomorrow. Wow. 15 minutes from now, we're going to take those skills and we're going to turn them into a multi-step process that allows you to predict whether or not a reaction is going to occur. So, for right now, I'm going to give you some practice to do on writing dissociation and predicting solubility, and then I'll give you 15 minutes to work, and then we will go ahead and put those skills to good use. Okay, so Chapter 14 review is on page 447, or it starts there. You're assigned numbers 1 and 2. No big deal, except number 2 goes parts A through J. It's okay. All you're doing in number 2 is predicting if it's soluble or not. You'll just use that solubility table that's in your book. If it is soluble, you need to write a dissociation equation. That's it. So I'm going to give you about 15 minutes to work on that, and then we'll practice putting those skills together. Okay, so you have done things where we mix two things. Okay, so you have possibly seen things where we take two clear liquids, we mix them together, and oh my gosh, we got to precipitate. It's a precipitation reaction. And what it means is that we've formed an insoluble product. So what we see is when we have two ionic compounds in aqueous solution, we can predict if we're going to get a precipitate or not. So basically we're predicting if a reaction is going to occur. The way we do that is very, very stepwise, and you can, if you want to just hang and listen before you start to write, you can. You write ionic equations for each of them, a dissociation equation. So you take the two products. Here we were told that we have ammonium sulfide and cadmium nitrate. Great. We write a dissociation equation for each of them. You know how to do that. Then you imagine that if these two things did react, what would the products be? You know how to predict products from a double replacement reaction. Then you look up the solubilities. Because while you know that you're putting these two things in an aqueous solution, we don't know if those products are soluble or not. If they're soluble, no precipitate. If one of them is insoluble, you're going to get a precipitate. So then we can write this double replacement with the states in there. So we know that cadmium sulfide, is insoluble. It's going to be a solid. Ammonium nitrate is, super soluble. It's not going to. What's going to happen is the cadmium sulfate will form a precipitate. It will come out of the solution. You'll have chunks in the bottom. The ammonium and nitrate ions are going to stay dissolved because ammonium nitrate is soluble, as was the thing that went into it. Okay, I have sodium carbonate and calcium sulfate. Sodium carbonate is soluble, and we're going to put this in an aqueous solution. Calcium sulfate, also soluble. We're going to put that in an aqueous solution. Oh, wait, I missed a step, didn't I? What does sodium carbonate dissociate into? How many moles of sodium ions? 2. So we get 2 moles of sodium 1+. We get 1 mole of carbonate 2- ions. These would all be in aqueous solution. What does calcium sulfate ionize into? CaSO4. How many moles of calcium ions? 1 is the loneliest number. Yeah. 1 mole of calcium 2+ in aqueous solution, and 1 mole of sulfate 2- also in aqueous solution. Okay, well that's easy. So we did the step of writing dissociation equations for both of our reactants. Now, if we had to predict, if we put these things in together and we said a reaction occurred, what products would you get? And this is where you want to remember back to, however you designate positives and negatives. So there always has to be a square and a circle. There always has to be a square and a circle. They're going to swap dance partners. It's double replacement. What would be your products, your potential products? What's one? Did I hear calcium sulfate? And of course, that would be Na2SO4. And what would be my other potential product? My other potential product would be calcium carbonate. Now, I do have to balance the equation. Is the equation balanced? I have 2 sodium on each side, 1 carbonate on each side, 1 calcium, and 1 sulfate on each side. So we're good, we're balanced, we don't have to do anything there. What do we have to do in terms of figuring out if we're going to get a precipitate out of this? Predict solubility! We're going to predict solubility. So, using your solubility table in the book, is sodium sulfate soluble? Okay, sodium sulfate is soluble, so this is going to be an aqueous solution. Is calcium carbonate soluble? Yes or no? The shells of sea creatures do not dissolve in the oceans. So are we going to form a precipitate? Yeah, we are. We're going to get a calcium carbonate precipitate out of this. This is going to go white and cloudy. Okay, that's the first 2 steps, and that's what you've already done. You know how to do this pretty well. So step 1, step 2. We're going to go ahead and go to step 3 just because it ties the other 2 together so nicely. What we're really putting in together in these 2 solutions is not sodium carbonate and calcium sulfate. It's a solution of these ions and these ions. So what we're really putting together when we mix these things in a beaker or a flask or whatever we're mixing them in is, what we're really putting in as our reactants, is all these ions just kind of floating around in their stuff. So that's actually the reactant side of our equation. I'm going to have to shrink this up a little bit just so I can fit stuff. What is the product side? Well, we know that some things just stay in solution. Okay, so what are our products? Well, the Na2SO4 stays in aqueous solution. Does that thing actually form a solid compound? No. Those things stay dissolved. So we come out on the other side with the same exact sodium ions and the same sulfate ions. And I'm just copying because I do still have Dissociation. I don't have to rewrite everything. Sorry to rub it in. Those stay in aqueous solution. Whoops. What else do we get out of this? There are 2 ions that we haven't accounted for. So what's the other thing we get out of this? Well, we get solid calcium carbonate. This is what's called an overall ionic equation. So we just wrote everything that happens here. And you've actually done every bit of this already because you know how to write a dissociation equation, you know how to predict solubility. So now you're just saying when we mix all these ions together, we throw all these ions in, these ions just keep swimming around, they don't hook up with a partner. These ions form a solid compound and they'll precipitate out. That's really the heart of it. There's only one step left to make what we call a net ionic equation. What is the difference between net and gross? Or net and overall? Who here gets a paycheck? Ever? From anybody? Okay. What's your gross pay versus your net pay? You don't know?
I only pay attention to the bulletin.
Okay. The one that you can put in your bank, and if it's for $100, they give you $100, that's your net. You made more than that before taxes.
Yes.
Your gross is before you take stuff out. Your net is what you're left with. In this case, this is our overall, it's kind of like our gross ionic equation. We look at any ions that really aren't doing anything. So we were talking about, friends who will help you come move your books. Have you ever been at some place where a lot of work's getting done, but there's somebody who's just not doing any of it? I have a friend like that, and every time that anybody had to move, he would show up. I don't think he carried a box, but he'd be there. He ate the pizza at the end. So, he was just spectating. No, moving's a spectator sport for him. If you're a spectator, you're just watching the action, you're not participating. In this case, are there any ions that are in the same form when the whole thing's over as they were in the beginning? Name me one of them. Maybe one ion that didn't do a darn thing. Same, you find it in the same condition we left it in. Sodium. So we can cross out sodium because it is what we call a spectator ion. Name me one other ion that didn't do a darn thing. It's in the same form when we get done with it that it was in the beginning. Sulfate? Yep. Sulfate didn't do anything. So really the only ones that did stuff were our carbonate and calcium ions because they actually formed a compound. So that's what we call, so now what we're left with is the net ionic equation, and we would actually say CO3 2 minus in aqueous solution plus Ca 2 plus, also in aqueous solution, forms, whoops, I cannot write today, I don't know why, forms CaCO3 as a solid. Because that's really the only action that happened, and that's our net ionic equation, so that would be step 4. Or step 5 if you call crossing out the spectators a step. But Tuesday, we will revisit this. We might have dry ice to play with. We'll see what happens. Who knows? Maybe we'll try and make an ice cream with dry ice. Do you guys all still get your school emails? Will you check those Monday night at some point? Okay. If we're going to do the ice cream lab, I'll just have you go get some stuff Monday night, and I'll bring some stuff and take care of it. But okay, that's sort of the highlights of this.